Then we're going to recap a little bit about combined stress. So combined stress is the analysis of structures where we have a combination between axial stresses and bending stresses. So we said that we are going to study columns in particular, and this in the first scheme we have in here. We see just a column with a load centered to the center of gravity of the cross section, so producing exclusively axial stresses that are calculated very simply, dividing the load, divided the area of the cross section, and they are negative because they are compressive forces, because this is a column and because the convention we have assumed. And after that, we had made some comments about the cases where this load, instead of being centered to the center of gravity, is eccentric. And we did the analysis of the three-dimensional column just to realize the way this work in terms of deformation and in terms of production of moments, and how the eccentricity produced this moment, and how the axial load P acts, producing axial stresses and bending stresses at the same time. We had said as well that well, when we have a combination of these two actions, when we have this column with this eccentric load, in order to do the analysis properly, it's better to decompose the effect of the axial stress with the load in the center of gravity, and the effect of the moment around the axis X in this case, but could be around the axis Y as well. And we mentioned that it's important, or it's very useful to have these diagrams that show the distribution of the stresses. This is the diagram for the distribution of the axial stresses because a load center in the centroid. And as you see, it's uniform. And this is the diagram for the bending stresses produced by the moment, because there is an eccentricity, where we see the linear distribution of the stresses, the compressive stresses on top of the neutral axis in this case, and the tensile stresses at the bottom of the neutral axis, which is the axis XX in this particular example. So if we combine these two diagrams, we can find easily the diagram for the combined stress. I will show you this for the exercises we covered in the previous hour of this session today. Well, the formulas are in there, doesn't matter. This is the case where the eccentricity is in the X direction. So it's similar to the exercise we covered, but with the load in the opposite side of the axis Y. But the idea is exactly the same. So we have the distribution of the axial stress, which is uniform, always in compression, and we have the distribution of the bending stresses because the moment My in this case is positive and produce compression to the right and tension to the left of the neutral axis, that is YY in this case. We have covered two exercises with numbers. So basically we have the case where the eccentricity is regarding the axis X, and the other case where the eccentricity is regarding the axis Y. So we saw that the axial stress is exactly the same because the load is exactly the same and the cross section is exactly the same. So loads divided by area is the same for both exercises. The only thing that changed is the value of the moment, not the value of the moment. The value of the moment is the same because the eccentricity in both directions is 50 millimeters and the load is 450 kilonewtons. What changed is the moment of inertia. In this case, is the moment of inertia regarding the axis X. In the second example, the moment of inertia was regarding the axis Y. And what changed as well is the distance to calculate or to evaluate the value of the bending stress, because in the first case, Y is equal to 250. And in the second example, X is equal to 150 millimeters. So, but the important thing to realize in this exercise is in this figure in here I have produced in paint. So, as I said, once you have the values of the axial stresses and bending stresses, you can produce, or you can sketch the stress diagram. So, for example, for the first exercise, where the eccentricity is regarding the axis X. So the load is located at this point in here. So you have a uniform distribution of the axial stresses equal to -3 Newton per square millimeter. And this is the distribution, the linear distribution of the bending stress produced by the moment that this produces because eccentricity and the load. So you have compressive stresses at the bottom of the neutral axis XX, and with the maximum equal to -1.8 Newton per square millimeter, and you have the maximum in tensile stress on top of the neutral axis equal to 1.8 Newton per square millimeters. So if you want to do the analysis in this fiber AB in here, actually here in the original cross section, you will have to combine -3 plus 1.8, and this is equal to -1.2. So you can have a diagram as well of combined stress in here, and with this value in this fiber in particular. And if you do the analysis, in the fiber CD at the bottom of the cross section, you have to combine -3, which is constant in every point of the cross section, with -1.8, which is the compressive force because the moment mx. And the summation of these two values, of course, is -4.8 kilonewton per square millimeter. Sorry. So the distribution of the combined stress is linear as the distribution of the bending stresses. And in this particular case is all compression in the whole section. So the minimum compression you have is -4.8 and the maximum compression -1.2. This is if you take in consideration the sign. You can say that in absolute values, the maximum compression is 4.8 and the minimum is 1.2. But the important thing is to know, is to understand that the combined stress have this linear distribution and has this value at this fiber AB and this value in this fiber DC. And it's the same for every vertical line we can sketch in here. So for every vertical line, the distribution will be exactly the same. Remember that this is a three-dimensional problem. And this is the reason why when we talk about a stress distribution, we are talking about a volumetric stress distribution. So this is just for a particular line, is a projection in some direction, but there will be a volume of stresses on top of this cross section. And in the case of the combined stress will be something like this. So I will just add in here for you to have after. So this is combined stress. This is axial stress. And of course, this is plus. And this one is bending stress. Okay. In the second exercise, it happened exactly the same. So you have the eccentricity regarding the axis Y in this case. So it's 50 millimeters, the same value of the force, etc., etc. But the axial stress diagram is something like this, and I put the diagram at the bottom of the cross section just because I'm doing the analysis around this axis Y. But you can put this diagram in the vertical direction in here as well, because actually the axial stress is the same in every single point of the cross section. So I will actually copy this one in here just to show that one more time that the distribution of the axial stress is the same in every single point of the cross section when we are talking about the axial stress. What happened with the moment around the axis MY, because the eccentricity now is in this direction, is that it's producing compressive forces in this half of the cross section and compressive stresses, and tensile stresses on the other side of the neutral axis, because the neutral axis is vertical in this occasion. Okay, so this is the distribution of the tensile stresses and compressive stresses produced by the moment My. And now, if we want to have the combined stress distribution of the stresses, we are going to have something like this, just because analyzing what happened, for example, in the fiber AC this vertical fiber in here, we have a compressive stress because the axial stress is equal to -3 minus 3 Newton per square millimeter, again because the bending. -3 is -6. What's happening in the fiber BD is something particular, just because the values we have in this case. In this fiber we had -3, and in this fiber we had 3 positive. So -3 plus 3 is equal to 0. And this is the distribution for this particular case, for this particular column with this particular cross section and loads and eccentricities in terms of distribution of the combined stress. The combined stress is linear. In this case, it's triangular because it's 0 in BD, and I reached the maximum of -6 Newton per square millimeter on the fiber AC, as you can see in the figure. So basically what you are doing summation of diagrams, uniform diagrams and linear diagrams that give as a result a linear diagram as well. Good. These are two very, very simple exercises because the eccentricities are only in one direction. But this could be more complicated, of course, because we can add more loads and we can add more eccentricities. And this is the idea of the third exercise you have in your notes. So basically, in the third exercise, in the third example you have in your notes, it says that you have the same cross section, but in this occasion you have the same load but located in another point. It's located exactly on the point B of this cross section is 450 kilonewtons. So you will have what we call a double eccentricity, because you have eccentricity regarding the axis X and eccentricity regarding the axis Y at the same time. Then what happens when you have this double eccentricity is that you will have a set of 2 moments instead of having 1 moment only. Regarding the axial stress will be exactly the same value, exactly the same distribution, and this doesn't change at all. But you will need to add in the combined stress analysis the bending stress produced by the moment mx, which is equal to 450 kilonewton times the distance from the load to the neutral axis, in this case is x, and the moment produced around the axis y, which is produced by the eccentricity and the loads in the horizontal direction in this case, because the neutral axis will be the axis y for the moment my. So in this case, you need to take more careful about what are the moments of inertia you are considering and what are the axes you are considering and how you are calling the moments, not to be confused, because you can be confused and have the wrong values. So in terms of area, the area is exactly the same as the previous exercises because it's the same cross section. So it's just the area of the rectangle. The moments of inertia you have to evaluate are both the moment of inertia regarding the axis X and the moment of inertia regarding the axis Y, but because it's a rectangle, this is extremely simple. So you just replace the value, you get the moment of inertia in both directions are the same as we calculated before. Anyway, the moments are the same as well. No, they are not the same because we changed the eccentricity. So now the eccentricity that is called EY, for example, is going to be 250 because it's half of the height of this cross section. The eccentricity EX is going to be half of 300, which is 150 millimeters. And this is why MY is equal to the load in newtons. So this is 450 kilonewtons times 1000 to transform to Newton times 150 the eccentricity. And this is the moment for My, the value of moment My, and this is the moment Mx around the axis X. As I said, the axial stress is exactly the same, -3 Newton per square millimeter, negative because it's compression and it's constant on the whole cross section of the column. But when you have to evaluate the bending stress in the extremes of the cross section for the moment around the axis X, you have to consider the moment of inertia regarding the same axis, and Y, the maximum Y is 250 because it's half of the height of this cross section in here, because this is the farthest fiber on top, or the farthest, fiber at the bottom. So you replace these values, and you get this value as a absolute value for the bending moment produced by the bending stresses produced by the bending moment mx. And you do the same considering this extreme, this x in the extreme to the left and to the right of the cross section is 150. And the moment will be my, then the moment of inertia will be iy as well, to be consistent. And this will be the value for your maximum bending stress produced by the moment my, which is the moment around the axis y. Okay, so you will have this set of stresses, the axial stresses, the bending stresses, because one moment mx, the other value for the stresses for the other moment my in this case, and you will have to combine them to analyze what's happening in every single point of the cross section. And we are going to do specifically the analysis for the points A, B, C, and D. But in order to do that, I will use a better diagram here. So I have all the values. So we have calculated the stresses, the axial stresses for the cross section when the load is centered, the bending stresses when the considering the moment mx, and we know that this value is an absolute value, so it's going to be positive 903 at the bottom of the cross section and negative at the top of the cross section, where we are going to have minus 903 Newton per square millimeter. And in the case of the moments around the axis y, we are going to have a bending stress of 8.96 Newton per square millimeter. This is not this is a bending stress, sorry. So compression on the right and tension at the left of the neutral axis y in this case. So having these three values, we're going to study all the combination possible in the four corner of this cross section, this original cross section. So just to add in here, I will add that this one is axial stress, just to be 100% clear. This is bending stress. And of course, the other one is a bending stress as well. I will move these values a little bit from here, something like this. Okay, so let's focus the attention to the point A of this cross section now. So I will work with this equation in here. So we are looking at the point A. So we are in this corner in here. So we know that at this corner, we have an axial stress equal to -3, because this is constants along the whole cross section. So there is no doubt about this one. When we check the point A for the moment, the bending stress produced by the moment mx, what we can see here is, because the moment is in this direction, the bending of this column will produce compression on top and tension at the bottom. So the point A is on top of the neutral axis, so it's going to be under compression. And this is the reason why we have a minus in here. It's minus this value, which is the value of the maximum bending stress. When we do the same analysis on the of the bending stress produced by the moment my, we realize that all this side to the left of the neutral axis y, we have tensile stresses. So this is the reason why this sign is positive in here. And if you do the operation -3 minus 9.03 plus 8.96, you have as a result -3.07 Newton per square millimeter. And this is the value of the combined stress at the point A in your original cross section subjected to the eccentric load P in the corner B, at the corner B. So You can do exactly the same analysis for every single point. So for that, so if you center your attention to this second point to do the analysis, you do exactly the same. So the first value, as you see, for every single case is -3 because this is uniform and this is constant along the whole cross section. So there's no any doubt about this one. In the bending moment produced by the moment mx at the point B, this is the point B, is exactly the point where we have applied the load. Compressive, the first one, no doubt. The second is compressive as well because the moment produces compression on top and tension at the bottom. If we focus the attention on the point B, in the case of the moment my, we know that this half is under compression and this other half is under tension. So using this code of colors in here is very, very helpful because we just can say, for example, this is blue, and this is blue. So all of them are negative. So it's -3, -9.03, -8.96, and the value, the combined value is -21 Newton per square millimeters. And it's very, very clear that this will be the maximum compressive tension stress on the cross section in this particular case. You can do the same analysis for the point C. So now we are analyzing the point C, this point in here, opposite to the point where we have applied the load. We have negative values for the axial stress, no doubt. We have positive values for the moments around X because we are in the area of axial stresses, positive axial stresses or tensile stresses. And it's positive again for the moments regarding the axis Y, because this moment produces compression to the right and tension to the left. So this is the reason why we have a minus, plus, plus. Minus is blue, plus is orange for C. So the value is 15 Newton per square millimeters in this for this particular point. Finally, if we do the analysis for the final point D, here is what we have. So we are at the point D now. So compressive, -3. This is positive because it's orange and because it's just doing the analysis again regarding the moment mx. We are producing tensile stresses at the bottom. And D is negative for the second moment because the moment is producing compression to the right side of or to the right half of the cross section. And finally, if we do the operation -3 plus 903 minus 8.96 is equal to -2 and 93 Newton per square millimeters. And this is the way you should be doing the analysis for every single exercise because it's exactly the same thing for all the problems we can have in this combined stress topic. And I will advise to do as well the diagrams. The diagrams I did in here for these cases can be done as well in both directions for this problem we have in here. So we are going to have a rectangular distribution of the stress, the axial stresses in here and in here. We are going to have linear distribution of the stresses in this direction for mx and in this direction for my. And we can combine these diagrams and to have a set of two diagrams in two directions for the combined stress in this original cross section, which is the interest for us because this is the analysis we are doing. So I don't know if everything is clear or if there is any question regarding combined stress. The secret for combined stress is simple to have a good understanding of how the bending works and how the distribution of bending stresses work because the axial stress is always negative. So the only thing we need to understand is where we have compression and where we have tension when we have a moment applied because this eccentricity. Well, variants in the for the exam could be to have other exercises with the loads in different locations. They don't need to be necessarily in the corner as you saw in the previous exercises. So the load can be in any place of the cross section, actually can be outside the cross section. So you can create your own exercises to practice this as many times as you need, because you can locate the load anywhere and you have a different exercise. The same thing is you change the cross section, and you can have rectangular cross section or any cross section, but rectangular one will be enough for you to study. But you can change the cross section and you change the exercise as well. And the other variant you can have is that you can have more than one load. So you can have, for example, a load in the centroid plus a load in the corner, or a load in the centroid and another load in here in the middle of the cross section, for example. This is the variation you can have. But for you to work by yourself and to try to challenge yourself a little bit and to see if you really understood what is the concept of the combined stress, I have created this proposed problem for you to practice for the rest of the session. So in this case, you have a column that I'm showing here the eccentricity in this way. So the eccentricity is 60 millimeters in any direction, because the cross section is circular, so it doesn't matter in which direction, X or Y. And this is the variation in here. So the cross section is circular, it's not so this is the cross section then. It's a circular cross section, and you will have to look for the formula for the moment of inertia. In this case, the moment of inertia regarding any axis will be the same. But I want for you to think as well in these free body diagrams I made in here for you, to think about the bending moment diagram, the shear force diagram, and the axial force diagram, and to calculate the reactions for this problem, to see how this works, and to realize that these type of problems are similar to the ones we did with beams. But the only thing is, because we are more interested in the stresses, we sometimes avoid the calculation of reaction, but we can calculate reactions for every problem. Actually, we do that when we analyze columns as well. So you have the data for this proposed problem in here. I have a question in here. So why do the plus and minus change in each? Well, this is what I have tried to explain during the whole session, this one and the previous one. So there is no clarity about how this works, I recommend to watch again this session that has been recorded, because this is what I have tried to explain. Because the whole point of these combined stress problems are to identify where we have compression and where we have tension. So the way of doing that is to think and to understand how this problem works in 3 dimensions. So I recommend to read carefully the notes from the beginning and to relate to the diagrams we have here, to the schemes we have in here, to the explanation, and you can watch again the explanation during the first hour today, and if you pay attention, you will find why we have compression in one case and why we have tension in others. So just as a matter of advice, try to see the way this deform. This is the key. If you see how the structure deform and how the moment produced these rotations around the different axes, you will see clearly where you had compression and where you had tension.